Hello everyone, welcome to Cheenta School of Statistics and Data Science. Today we'll be looking at the first problem from the CMI MSc DS entrance from 2020. So we'll be looking at some questions based on linear algebra from the MCQ paper. Alright, so the first question looks pretty simple to look at. So here are two matrices, and we've been asked to check whether which four of the given statements are true. Now you can see the answer though, like the ticks and crosses. But what really matters is how we approach these questions. So let's first just look at these two matrices once, because then we can get quite a lot of useful information. So the first row of A is basically 4 zeros and 15, right? And you can just see this is a very nice pattern. This 1, 2, 3, 4, 5 on this row. And there's 6, 7, 8, 9, and 10, 11, 12, 13, 14, and 15. And then this P. So okay, so just look at this from this angle now. Take this column and take this column. Swap them. So what are you going to get? You're going to get 15, 14, 12, 9, 5, and whatever comes here, and you're going to get 0, 0, 0, 0, 1. Right? Now take this column and swap them. It's nothing but this one and this one, right? So when you're swapping them, you're going to get the 15th column, and then you have the 0, 13, 11, 18 thing. It's 0, 13, 11, 18, that column. Then you have the middle column, this is 0, 0, 10, 7, 3. Then you have the 0, 0, 0, 6, 2, and then the other column, which is the 0, 0, 0, 1, right? So take a look at this matrix that we have right here. So actually, what I'll do is I'll just write this a bit clearly to make it easier to understand in this case. Just give me a second. Yes. So initially we had landed up with this as the first column, 12, 9, 5. Now by interchanging this row, we're landing it as this. Let's write this entirely 8 and 4, and the middle column stays the same, 10, 7, 3, followed by this column 0, 0, 0, 6, 2, followed by 0, 0, 0, 0, and 1, right? Now look at this matrix and B. You can see the first column in B looks like kind of a mirror image of the first column of this matrix. If you swapped the first and last rows of this matrix and then the second and fourth rows of this matrix, you'd essentially end up with B. So you can see that you can get B from A using a series of linear transformations. Not my bad, not linear transformations, my bad. You can go from B to A following a series of elementary operations. Elementary operations is something that you did in class 11 and 12, which consisted of basically elementary row operations and elementary column operations. In elementary row operations, you would do one of the three following operations, which are basically you would swap two rows, or you would add a multiple of one row to another row, or you would divide or multiply one row with a scalar. Each of these three operations would result in some change of the determinant of the matrix. One of them being that if you interchange the rows of a matrix or interchange columns of a matrix, the sign of the determinant would flip, right? So if you have a matrix A, determinant mod A, determinant A, right, and you swapped two rows, that is say row 1 and row 2 of A, then the determinant would become negative of the actual determinant. Again, you swap something else, then that sign you can flip to back to the original one. So even number of the switches will generally result in the determinant staying same. So now we will be using this fact later on. So the first thing that we are looking at here is determinant of A is equal to determinant of B. Okay, so we'll come that to later. Okay, so let's just look at option B first, because option B is easier to do. Here's they said that trace of A is trace of B. The claim is that trace of A is equal to trace of B. So I'll just erase this. So how do you define trace? Trace is nothing but the sum of the diagonal elements. In this case, it is 0, 0, 10, 8, and 5. Sum them up, and this will turn out to be 25, which is this. For B as well, it's 5, 8, 10, 0, and 0. Sum them up, and you end up 25. So it's actually B. So you see that trace of A is equal to trace of B. So option B holds. Next, just what I mentioned, note that we can get B from A by the following elementary operations. I don't say elementary row operations because we perform elementary operations on both columns and rows in this case. So what is the first operation? We swap columns A and 1 and 5 of A, which we did here, this one, you can see. Then we swap columns 2 and 4 of that intermediate matrix, then we get this. And then I showed you that we can swap rows 1 and 5 and then 2 and 4 to get the matrix B. So it's here. So this is 4 swaps. So basically 4 series of sign flips in the determinant of A. So the sign flips when you multiply the determinant by -1. Since there are 4 operations in this case, so determinant of B basically becomes -1 to the power 4 into determinant of A. Again, I'll repeat why. So in this case, determinant of A was this. You swapped column -1 and 5, and the determinant became this. Then it became this, which basically I'm multiplying by -1, you have to flip the sign. Then this, ultimately this. So 4 operations. So if we multiply by -1 4 times, but -1 to the power 4 is nothing but 1. So determinant of B stays the same as determinant of A. Thus, option A holds. Now, if option A holds, automatically option C is ruled out because determinant of A is not 0. You see, x equal to y and x equal to -y holds only when y is equal to 0 is equal to x. So in this case, this would have held if determinant of A would have been 0. But since this is an basically, this you can see this okay, just look this. Look at this. This is a upper triangular matrix. Since the determinant are the same, so determinant of A is determinant of B, and determinant since B is an upper triangular matrix, then B's determinant is nothing but the product of its diagonal elements, which is not 0 in this case. So definitely these are not singular matrices. So option C is ruled out. Now moving on to option D, we can see that option D holds because trace of AB is equal to trace of BA for all real matrices A and B. The reason that I'm using this and I'm not proving any of proving this statement here is because there are some properties regarding the determinant, regarding rank, and regarding trace of matrices. Some very simple properties which are easy to mug up, and in a certain way very easy to prove as well, that you should have them prepared in your memory before this exam, because very simple questions, especially in the objective part, that is in the multiple choice questions part, comes from linear algebra, which uses this property, whose solutions use these properties of trace, rank, and determinant, and they're usually very easy to solve if you remember these properties. This property is a very common property, that trace of AB is trace of BA. This is as common as determinant of AB is equal to determinant of A and determinant of B. There are similar properties for rank as well. So always remember these properties, and if you remember just that this property holds for all real and also complex matrices A and B, you don't even need to calculate this or try to prove it for this specific case A and B. You just know that this holds for any AB, so this will hold for this AB as well. So basically option D would be kind of a free for you if you remember this property. So one of the key takeaways from this question is, when you see these large matrices, when you see very large A and B and such matrices, always, and they look kind of same, they have the same elements, and there's a pattern to them, always try to check if there's some if you can get one matrix from the other using some series of elementary operations or not. Because if you can do that, then you can use the properties of elementary operations that the determinants and stuff, and you can derive whatever is asked in the question very easily. And also, let's remember the properties in the first place. The properties are very easy to learn. They're available on Wikipedia. If you just go to Wikipedia and just search reservoir matrix, look at the properties, just learn them up. So moving on to the next question, and variation, like this question is special in the sense that variations of this question comes in competitive exams for statistics at the, like, for postgraduate courses for IIT JAM, MS, and as well CMI's entrance, and in many cases in MSET as well. I'm not sure about that, but yeah. So variations of this question comes in many of these entrances, like, and you'll find like the pattern of this question is very similar to a very popular question that really appears in all sorts of mock tests and stuff. So let's go with this question. It says that suppose that A is a n cross n matrix with n equal to 10. Now look at this first line. I'll pause here because look at this. You have n equal to 10. When you read the question, you'll find that nowhere you have to use the value of n. This n equal to 10 is nothing but a distraction. A distraction, it distracts you from what information in this question is actually important. So just ignore n equal to 10. This question, it applies for any arbitrary n. Like if they had given n as 5, 2, 3, 4, whatever, this question would have remained the same in a sense. So just ignore that with n equal to 10 part. And B is an n cross 1 vector. Suppose that the equation Ax equal to B for an n cross 1 vector does not admit any solution. Right? It says that Ax equal to B is a system of linear equations. You know, you have a given B and you have a given A. Like A is already given. And Ax equal to B does not admit any solution for X. For B. There's no X which satisfies this equation. So which of the following conclusions can be drawn from this information that we have? First one is that A inverse does not exist. Second one says that the equation A transpose X equal to B also does not admit any solution. The third one says that determinant of A is 0. And the fourth one says that suppose there is another C for which again Ax equal to C does not admit a solution. So it basically says that Ax equal to B does not admit a solution X. X equal to C also does not admit a solution X. Then B and C must be a constant multiple of each other. That is, C, that it basically claims that C is a constant multiple of B. So we need to verify which of these four conclusions hold, right? Now we'll go one by one. First one, Ax equal to B does not have a solution. Right? Assume that A inverse exists. One of the ways to approach these kind of questions is try to prove it by contradiction. Now you definitely know that if Ax equal to B does not admit a solution X, and if A inverse exists, suppose A inverse exists, then we can multiply both sides from the left by A inverse, right? We can, if we have Ax equal to B, we can multiply both sides from the left with A inverse, right? Like this. And then A inverse A is obviously identity, so this part becomes identity. So this part is nothing but X. It says X, and this is A inverse B. Now this thing becomes the solution of this equation, right? And if this thing becomes a solution, this is basically a contradiction to whatever information we were given. So A inverse cannot exist. It's a contradiction. So A inverse does not exist. You also know, like from your 11, 12 days again, and from linear algebra you learned in your undergraduate courses, that if a matrix does not have an inverse, that means it is singular, which means that its determinant is 0. Right? So a matrix that is singular has a determinant of 0, and it also doesn't admit an inverse. So automatically from A, C also becomes true. Determinant of A is 0. That is, A is correct, and from A it follows that C is also correct. Let's look at B first. The equation A transpose X equal to B also does not admit any solution. Right? So again, we have been working with counter examples, and you can see that it's not exactly easy to prove this, that A trans, like, so I'll give a hint why we kind of intuitively understand that B cannot be true, right? That why B actually should not be true. Look at this kind of matrices, A that I have, right? Which has just one column as 110 and the other two columns are all zeros, right? So think about like these matrices exist as well, and that always remember that when you are considering a system of linear equation Ax equal to B, it is kind of like A is kind of like a linear transformation from some vector space to another vector space. Okay, think of it as a function from a set of vectors to another set of vectors. Okay, so those who are not familiar with linear transformations, think of it as a function, right? So it says that this function A has a domain set of vectors and a range set of vectors, and for some vector in the in the codomain set, there is no corresponding vector in the domain set which maps there. That is what Ax equal to B not admitting a solution for B is basically. A transpose is also another such function, right? A transpose is also another such function that goes from the same set to the same other set, right? But then if A does not admit a solution, you cannot really say that A transpose won't admit a solution. And this has got nothing to do with A transpose also not having an inverse. So let's just look at this counter example. Say n equal to 3, and for this very reason, I said that don't even take into account that n is supposed to be 10. That is just rubbish. That is a distraction. So have A equal to 1, 0, 0, 1, 1, 0, and 0, 0, 0. And consider B to be this vector, which is 2, 0, 0. Right? Does Ax equal to B have a solution? Let's look at it. So consider Ax equal to B and x to B is 1, is 2, is 3. Then what is X? It's nothing but x1, x1, 0. If this is a solution, it has to be equal to this. Equate the elements. X1 turns out to be 2 and x1 turns out to be 0. Is this possible? Nope, definitely not. So this does not admit any solution X. For this A and for this B, there's no solution X. But A transpose, look at A transpose. A transpose is 1, 1, 0, 0, 0, 0, and again 0, 0, 0. So A transpose X equal to B has a solution. How? I'll just show how again. So A transpose X is what again? 1, 1, 0. It's nothing but x1 plus x2. Okay. Then it's 0. Then it's 0. Right? And here you have 2, 0, 0. This has a solution 1, 1, 0. You can multiply it and see that it is 2, 0, 0. So this has a solution. So obviously B is false. You see that A transpose X equal to B has a solution and Ax equal to B does not have a solution for the same A and B. So B is false. Finally for D, let's look at D. D says that if C is another vector for which Ax equal to 0 does not have a solution, then C has to be a constant multiple of B. What this actually means that B and C are linearly dependent. It claims that if X equal to B and X equal to C does not have a solution, then B and C must be linearly dependent. But it may not be the case. It may not be the same case. And how do you understand that? I'll just give an idea again. Consider the matrix A. So like I was saying about linear transformations, A, like A is an n-cross matrix. So A can be taken as a linear transformation from Rn to Rn, which is nothing but all n-cross-1 real vectors. This is all n-cross-1 real vectors. That is what I mean by Rn, right? This is nothing but a function from this set of all n-cross-1 real vectors to the set of all n-cross-1 real vectors, right? The image of it, that is, what is the set? Ax for all x belonging to R. This set is actually a vector space and a subspace of Rn. And this is something that you should be familiar with if you're attempting this exam, because knowing this concept, this is a very basic concept of linear algebra, and when you start learning matrices, and like I believe that you should be learning how matrices relate with how matrices relate with linear transformations, because this just makes a lot of questions very simple to understand. So, so I like this whatever I'm saying right now is kind of like I'm giving the kind of like an intuitive understanding of why those B and C may not be linearly dependent. And so that's what it is. So imagine that this entire circle is Rn, and this part is the image of A, right? And the remaining part won't have a solution to the equation Ax equal to B. The remaining part won't, because they don't follow, they don't fall under the like inside the image set. So take a subspace of the remaining part. So this is another subspace of the remaining part. Okay, and then take its basis. So the basis vectors are always linearly independent, but neither of those two will have solutions. So so you don't always have B and C to be linearly dependent. That is what I will show in this counter example. Take A to be this matrix, right? Just the 1, 1 is entry is 1, rest every entry is 0. And then for all x belong to R3, Ax is of the form some constant times 1, 0, 0, right? It's of the form some constant times 1, 0, 0. And so this things is nothing but matrices that fall under image of A. So Ax, so the set Ax, that is an image under A, is nothing but the span of this vector 1, 0, 0, which is a subset of R cube, R3, my bad. Obviously, 0, 1, 0 is not not an element that falls under this span. 0, 0, 1 is not also something that falls under this span. 0, 1, 0 and 0, 0, 1. Why? Anything that belongs to span of 1, 0, 0 is a constant multiple of 1, 0, 0. 0, 1, 0 is not a constant multiple of 1, 0, 0. 0, 0, 1 is also not a constant multiple of 1, 0, 1, 0, 0. This is because these three forms are basis of R3, so they're linearly independent, that you should know from beforehand. So these two does not fall under these bands. And obviously Ax equal to this and Ax equal to this do not admit solutions, that we have already seen. These two do not admit solutions. And these two are linearly independent. So our option, like our claiming D, is also false. So that brings to the end of this video. I'll see you later, and thank you.